Hello, this is Dr. Prasad Putilam on my YouTube channel, My Intuition 4865. Continuing the class series of Applied Physics for Computer Science stream under Visvesvaraya Technological University with subject code BPHYS 102 for first semester and 202 for second semester. Okay, so I'm moving to the part 3 of module 1 about lasers and optical fiber applications. The same syllabus it is applicable to other universities also, but the syllabus I took from the VTU website and taking the classes, and this class is for not exactly for exam point of view, only to understand the applications more details I'm giving. Okay, so for thank you for subscribing to my YouTube channel. That is the only support that I expect from you people, and many are supporting me daily. Your support I can see. So I'm happy with that. Please do subscribe if not subscribed. Please do share the video to others. For that it will be useful for them. Okay, so moving to the laser action, population inversion and metastable state. Considering to explain that, I'm considering the core of an atom. A core of an atom always is having a positive charge, so represented with the positive charge, that is a core of an atom. And there are electrons in a given spherical way. The electrons are able to rotate with the positive charge center at the center of the atom. Surrounding that, negatively charged electrons are revolving and they are in a stable state. Okay, so you can say that electrons are continuously moving. I cannot say on which direction or what type of movement it is there on surrounding that positive charge. There is an electron cloud. I am represented here. One electron I have represented here. Okay. Now suppose if a photon is given to that atom. So you represent a light source here, then representing with a photon. So you can see that small dotted one, that is photon. Okay, so I think uh, this one. Okay, it was very difficult to identify a small spot. Okay, a photon represented with a particle now, because but photons are not having only particle nature, it is having wave nature also. Therefore the photon it is traveling to the atom or near to the atom in a particle as well as wave nature. It comes there, it hits the atom, or the electron absorbs the photon. When the electron absorbs the photon, it will jump to a higher energy level. So represented here that a photon is coming, it is being absorbed by the electron. When electron jumps a photon extra energy, therefore it will go to a higher energy level compared to the previous state. It will go to a higher energy level, and that is the electron with the photon energy. So we call it as absorption and excitation. Okay, so previous one you can say that it is absorbed. Here in this state it is absorbed, then it is moving to a higher state, a little bit away from the center, so a higher energy state, which is called the excitation of of the electrons. So absorption and excitation is roughly represented here right now with this schematic way. Okay, now this electron which is in excited state means they are always higher energy, means it always want to become stable, means it want to lose that whatever extra energy that it has got, it want to lose it, and it want to go back to the normal stage where normal space where it has got more stability. So when it comes back, that is called emission. Okay, it loses that photon, and the photon goes away, so it emits the photon and go back to the normal ground state or normal state where it is supposed to be. So this is called absorption, emission, absorption, excitation, and right now what you see, that is a representation of the emission of the photon. Okay, suppose if the electron is already in excited state, so electron is in excited state with that one photon. If another photon comes, see another photon. Okay, so if another photon comes there to hit that, or coming in that way of that electron, if one more photon comes there and it comes and hit there, what happens? The electrons will go back to the ground state. From the excited state, the electrons will go back to the normal state. the photon also will be released, and the released photon is equivalent energy with that of the photon which is coming. So this photon coming in this direction, in this particular direction, with this particular wave nature, I can say. So when it releases that, two photons are now, one photon which was coming and hitting that atom, another photon which was already there with the electron, both will go in the same simultaneous, just synchronizingly it will go, which is called as the coherence. Okay, I used the word coherence in my previous class video. So here this is can be connecting to that. When a photon comes and hit the excited electron, the photon is released with the hit the photon which is coming, both will go in the same direction, same pattern, same wavelength, everything in the same way, same fashion it will go. We call it as coherence. Therefore a coherence occurs. This is called stimulated emission. Okay, so here the emission takes place, the photon is emitted, removed from that electron state, and that is from the excited state, with the addition of one extra photon. When it hits there, the emission takes place. That is called stimulated uh, emission. This is what Einstein introduced as extra, and this is the main thing which is needed for the laser action. So it's a stimulated emission. So stimulated emission, where the stimulated emission in which the photons, both the photons now are in a coherent state, and they are having same direction, they are moving in the same direction. I will keep on moving in that same direction only, unless until somebody push them back. Okay, now if the electrons when it get excited, it reaches to a initial excited state, but compared to the initial excited state, I can represent somewhat here. It was here. Okay, it was here. That is the initial state, not the metastable. Metastable, keep it there. This is the normal exciter state when a photon comes and hit, but it takes to a metastable state, because this is more energy state, and ground state it is somewhat here, this particular area. Okay, so it will go to a space, it go and occupy a space in between that of the ground state and the exciter state, a little bit lower energy state than that of the initial state, but a higher energy level compared to the ground state. That stable, where it can remain for a longer time. So the word used is, it stays for a longer time. In an excited state, it stays in a longer time, and it is not the initial excited state, in between that of ground state and higher and initial excited energy state. That stable state, it is called metastable state for an electron. Okay, so this is the term metastable state, which I have explained now. Suppose if many of such atoms are absorbing the photons and going to a excited state, but which is a metastable state. So these are all metastable states presented here. 1, 2, 3, 4, 5 metastable states, and one atom it is in ground state only. Okay, such situations in which majority of the atoms are in excited state with the photon, and that too in metastable state. Even if it is not metastable state, okay, majority of the population is in a reverse case, inverse case, not the normal case, inverse case. We call it as population inversion. Okay, so this is the condition called population inversion, when photon light energy falls on atoms. Okay, whenever I say atom, it is not one atom. One atom is very small. There will be a lot of atoms present in nearby. So majority of the atoms are going to the excited state with this type of situation. We call it as a population inversion. So this is just a schematic representation. Don't think that this diagram is a population inversion. This is schematically representing. Okay, imagine that state in which most of the atoms are in excited state, the electrons are in excited state with the photon absorbed, which is called a population inversion. Okay, now the after when the photon hit the uh, electron at the excited state or metastable state, it releases the and another photon, and they go in coherence, same direction, same wavelength, everything. If you keep a mirror, a 100% mirror, 100% opaque mirror, which will reflect completely all the photons, all the light, and I'm keeping another mirror on the other side, opposite side. Okay, so one mirror I kept here, another mirror I kept here, and the second mirror is around 95 to 95% only. It is opaque, means 5 to 2 to 5% it is transparent, the light can go out, photons can go out. Okay, so I made a situation which one side it is highly 100% transparent, 100% opaque mirror, and the other side it is around 95% opaque only. Means 5% it can transmit. Then it is kept inside a tube, and now we are creating a cavity here with the atom which are capable of getting excited to higher energy level, capable to release the photon when called a stimulated emission. Such a situation, if it is created, then all the photons will be traveling back front, because reflection is there. Even if it go to the left side, there is a 100% reflection mirror is there. If it go right side, only 2 or 3 or 5% only can escape, remaining 95% can should go back. And there are in between, there are atoms still, the atoms are absorbing the photons in between, going to higher energy level, again another photon will come hit, it will release another photon, stimulated emission takes place, metastable state it reaches. So there is a continuous increase of the photons which are traveling in the same direction, same wave nature, or whatever the wave number, we can say they are all in coherence, and there is a population inversion is there, metastable condition is there. There is a stage in which there is an increased number of photons of same direction, same wavelength will push out from that, only 2 to 5% from that cavity, but it comes out as a very intense light, which is called as the laser. That is called laser action. Understood? No. Okay, so this is the way how the laser works, roughly schematically represented. If I take a better example, better imagine, say images, if I take, say this is the stage in which a mirror is there, two mirrors are there, one is called output mirror, and there are atoms, they are getting, emissions are happening. Emission means that movement of electrons, movement of photons represented here. A second stage, that some light it can come out from the cavity, and when it reaches the right side end, that is again reflection takes place, some of the light come out, but again when it go to the left side, you can see the number of photons are getting increased, but all are synchronized, all are coherent. Again strikes the right side, more excited atoms are still there, coming to the right side, again go into the left side, even the number of uh, photons increased, number of photons in the same condition. So this is the population inversion almost stage, and more intense laser is coming out from that, and further the number of photon increases, and finally the equilibrium stage comes, and there is a high intense laser coming out, and at this stage onwards it will be continuous laser beam of will be coming. So this condition it will reach immediately as soon as we switch on that laser switch, whatever we call it. Immediately there is an lamp connecting to that cavity where the atoms are kept. So that lamp will glow first, means it will give some photons to that inside that chamber, cavity chamber. There it hit the atom, electron jumps to higher energy level, jumps back with emission, more photons are released, again photons comes reflect from the mirror, then coherence happens, population inversion happens, suddenly the laser light will come out from that device. So everything happens within fraction of seconds. So this is the working of roughly the working of a laser action. Working of a laser is called a laser action, and this image I took from Encyclopedia Britannica. Copyright is there. I'm not claiming any copyright for this, just for education purpose. Please. Sorry for taking this image. I didn't get any other better image. So this is the image which I found very interesting, very easy to understand. So this is the schematic setup of a laser, and this is how the laser beam comes out from the laser. Okay, now laser action in words, whatever it is with the images. Now I am going to read. Don't worry, I am going to read. This is the different steps or critical steps which involve, which called as the working of laser or laser action. First one, that is the excitation of pumping the medium. In this step, energy is supplied to the medium, which can be a gas, a liquid, or solid, the medium. And this is called pumping, and it excites the electrons of the atoms medium to energy state. Energy can be supplied in different ways: by electrically if it is a gas laser, optically if it is a solid state laser, or chemically if it is a dye laser, if the laser, the atom is made of dyes. Different colored dyes can also be used in laser. The second stage, that is reaching the metastable state. A metastable state is a temporary excited state of an atom or ion or molecule where it remains for a longer period than usual before transmitting or transitioning to a lower energy state. So this delay in the transition is key to the operation of many laser and other physical processes. One extra dot not needed. Okay, so that is the requirement, metastable state, a temporary state that is needed, a small delay needed, so that more photon will come and stimulated emulations happens continuously. Then comes the population inversion. So in normal system, the electrons are in lower energy, which is called the thermal equilibrium. But for a laser to work, we need atoms in excited state. That too, if it is in metastable state, is more important. And this condition of the existence of an atom in an excited state is called population inversion. More number of atoms are in excited state, we call it as population inversion. The population, it is inverted, the reverse case, not the normal case. That is the word meaning population inversion. Population inversion is crucial because it allows stimulated emission to donate more spontaneous emissions. Without population inversion, most of the atoms would relax back to the ground state via spontaneous emission, producing random photons and not the coherent light. Therefore, the population inversion is very important. Reaching that population inversion is very important. Then comes the stimulated emission. This is the heart of laser operation. When an electron in an excited state interacts with a photon of the same energy, it falls to lower energy state and stimulates the emission of another photon. Okay, so you know the full form of laser, LASER. In that itself, the stimulated emission word comes. Therefore, that is the heart of the laser operation. So the result of the amplification of light, the more stimulated emission occurs and more intense the laser beam becomes. Then comes the optical point optical cavity. Optical cavity, the sustaining process. The photons are bounced back and forth between two mirrors in a structure known as the optical cavity. One of the mirror is partially reflective, allowing some light to escape as the coherent laser beam. As the photon reflect back and forth, they stimulate more emission from excited atoms, leading to build-up of coherent light. Then comes some of the examples, which type of materials are used. This is not there in syllabus. I added extra only for information, so that engineers can get benefited from that. Which type of molecules are used. There are different type of materials like solid state lasers. We use neobidium dot yttrium aluminum garnet. That is, neobidium is the atom, and it works in a wavelength of around 1064 nanometer. That is infrared. Infrared light has to be of this wavelength light. If it is used initially, then only this particular laser will work. So the application, this is used in material processing, medical surgeries, and the range finding applications. Then comes the ruby laser. Ruby laser is very famous. Okay, so the atom used is chromium doped sapphire crystal. So it look like ruby, that word, because of that. So common wavelength used is 694 nanometer. That is red color. It is used in holography. It is used in research. It is used in dermatology. Then comes the gas lasers. Gas lasers, helium neon laser is there, carbon dioxide laser is there, argon ion laser is there. So in helium it is 632.8 nanometer. It is used in laser pointers, alignment tools, laboratory equipments. Carbon dioxide laser, it works at 10.6 micrometer, that is infrared range. It is used in cutting, industrial cutting and welding. So mainly for the mechanical engineering students, they should know that it is carbon dioxide lasers are used. Okay, mainly cutting applications, uh, welding applications, even medical therapies. Then argon ion laser, it is works at 488 nanometer. It is blue range, or 514 nanometer, which is green range. It is used in medical procedures, spectroscopy, display systems. Then comes the semiconductor laser or diode lasers. Material used are gallium arsenide, indium phosphide, gallium nitride, in which gallium arsenic, indium phosphorus, nitrogen, these are used. So a variety of the wavelength varies from 650 nanometer to 1550 nanometer uh, for this application and for this particular laser, and it is used in optical communication, consumer electronics, medical devices. Such cases, the laser used is diode lasers or semiconductor laser. Then comes the dye laser. Dye molecules such as rhodamin 6G or coumarin are used, and it works in a visible spectrum because they are dyes having they can absorb the visible color. It can emit the visible color. Therefore, it is used in spectroscopy, research, and medical fields. Fifth one, that is excimer lasers. Excimer lasers or excited dimers of inert gases and halogens are used, and it works in a wavelength of ultraviolet 163 nanometer for AR. And application, it is used in the LASIK, the eye surgery, means cutting the thin layer of the eye and then using laser to shape the eyeball, the lens, eyeball lens, that is called a LASIK surgery. For that, this particular excimer laser is used, a very important one. Recently my father and mother both completed LASIK, and I am waiting for another 20 years to get a LASIK surgery. Okay. Then it is used in microlithography also. Sixth one, that is free electron laser. Material high energy electrons, not traditional atoms or molecules, are used in free electron lasers. They are having wide range X-rays to microwaves. They used in scientific research, imaging, and particle physics. So mainly study of physics. Further, it is used. Okay, okay, that's about laser action. Then what? The population inversion, metastable state, those things are there in syllabus. These are additional extra information, and I'm giving those because you are like me, and you are subscribing these YouTube videos. My intuition 4865. You are sharing my videos to others and getting benefited from me, also getting benefited. People who are watching, they are also getting the information in a structured way. Okay, information I collected from internet only. It's not that what I made separately, but arranging it in a way which is useful for the audience. That is my work. So you are supporting me for that. Thank you very much for having a subscriber to me, and have a nice day. Thank you very much once again.